Hello, everyone. So this is Yang Jun from Uber. And in this topic, I will work with Beinan to share how we build a petabyte scale of cache for Presto. Yeah. And in this topic, we will cover the motivation and challenge and introduce the distributed cache Alluxio. And then we will share two phases for us to build such a distributed cache. One is on-premise, another one is cloud. Then we will show our plan of the next step. Yeah, let's start from the storage and process scale at Uber. So the storage here means data lake storage. So in HDFS, especially in HDFS, we have to express data, the physical data footprint in HDFS, and the peak rate throughput can hit 3 kilobytes per second. And Presto is the dominant contributor, so it can contribute more than 70% of the rate at the peak, and it can read more than 300 PB every week. Yeah, so Uber is in progress to do massive migration from on-premise to cloud. So during the cloud migration, we encountered lots of challenge. So that's our motivation to build the on-premise cache. For on-premise, so we have one big issue is that due to some non-negotiable requirements, the migration progress of the storage and the computing, they are different. So for example, in 2025, we decommissioned more than 50% of the storage node in HDFS. So in that, but we at the same time, we still have large portion of the Presto query in on-premise. So the HDFS cluster were overwhelming and Presto encountered lots of read slowness. That's why we need to build a distributed cache so that we can reduce the read from HDFS and also do traffic shaping for the heavy users. And then on cloud, Uber is somehow the elephant in a new GCS region. So we encountered the GCS egress challenge and also got throttled where we read too much data. So at another hand, the cloud object store, it has both storage cost and also file access cost. If we have the cache, right, we can reduce the file access cost. Yep. So here is a quick introduction for the Alluxio. Yeah, this diagram is I got from the Alluxio website. So Alluxio is a popular open source project. So some top advanced feature is that it's decentralized. It can support page level partial file cache, and it has the linear scalability. Yeah, we can cover that part in following slides. So here is the architecture overview for our project. The Presto, majority of Presto are still keep the same, especially for coordinator, right? And the integration happening at the Presto work site. We update the storage client a little bit so that it can read the hot data set from Alluxio cluster. For the non-hot data set, it will read to remote storage directly, like the HDFS or GCS. So if Alluxio cluster don't have such file, right, it will pull the file from the remote storage. Let's move closer. So this diagram shows how we integrate with the Presto worker node. So, yep, the key part here is that Alluxio worker is a decentralized cache node. It will register themselves to the etcd and maintain the heartbeat for the node liveness checking. So for the Alluxio client at the Presto node, it will pull all the cache node from etcd and then build hash ring so that it can route the traffic by the file ID. In that case, we can support the linear scalability. And the Alluxio master node is somehow like not on the critical path. Yeah, so that's why we don't have a single point value. Yep. Let's move closer to show how we store the cache. Yeah, that's the architecture we for the cache worker in Alluxio. So it has two key endpoints in the cache worker. One one endpoint is for the metadata. So in that case, we can get a file info from the Alluxio. And another one is the data rate endpoint. So it's served by native data server. Yep. So within the Alluxio worker, we have a file metadata store. That's for the file metadata. And we have the paged file cache is just in the local file system. And then we have a in-memory page method index so that we can check how which file ID has how many pages in the cache. Yep. So the Alluxio worker can evict the file if the config capacity is full. So in practice, we leverage the LRU to do that. Yeah, the underlying file system can be HDFS, GCS, or AWS. Okay, so that's the one. So for the on-premise part, so yeah, again, for the on-premise cache, right, we focus on to reduce the data rate from HDFS. And also we are trying to integrate with the Presto so that we can build Alluxio cache cluster in Uber, right? That's somehow like our first project. So yeah, this diagram is to show how we integrate with the Presto, Alluxio, and HDFS. So we named it as tiered file system because Presto, we have the local cache, and we have Alluxio remote cache, and for the remote storage, we have HDFS here, right? So we will when we got a file read request, we will try to read from local cache first, and if it is not in the whitelist, right, we will read from the Alluxio file if it's in the whitelist. If no, we will fall back to HDFS. And in order to make it more flexible, we have built some feature like in-flight configurable cache allow list so that we can turn on and off the cache on demand, and also update the hot table and partition list. So we also built some security feature so that to protect the traffic from Alluxio client to the Alluxio worker. Yep, and here are more features. So when we adapted the Alluxio cache into Presto, we encountered lots of issue. Why is that? Because in Uber, when we have the Alluxio cluster, we have some other automatic operation, especially to replace the node to do some security patch or just fix some hardware issue, right? So the rate from Alluxio is not always reliable. So we implement something like the for backable input stream. So in this diagram, right? So when we read from Alluxio, right? If anything wrong at the Alluxio worker or at the network layer, we will fall back to the GCS input stream, data input stream. So that can improve the reliability for the Presto query. And there's another issue is that we identify there are lots of small we identify the file access pattern in Presto is somehow like easy to be interrupted or terminated. So which has some side effect at the server side. The server side, it may have the thread link. Because the current implementation in the Alluxio worker, it is somehow like stateful. It depends on some clear signal from the client side to cancel the request. Okay, or terminate the state machine in Alluxio work side. But because Presto, when the query read enough data, with sufficient data, right, it may terminate the query, or it may just return the result to customer directly. Then in that case, the file read status is somehow like a non-deterministic. So in that case, at the work side, we implement some mechanism to proactively release some state machine or release some resource at the work side. In that case, we can prevent the thread leak at the server side. Yeah. And besides that, we encounter another issue is that the small file read in Presto, because in Uber, we have lots of packet file. So when we run query against some packet file, right, we may have lots of small read in metadata, and also we have column level encryption, which may also result in lots of small read as well. So in order to adjust at the very beginning, the small read is somewhat like a block issue for us to launch the Alluxio distributed cache, because the Alluxio worker was overwhelmed by too many requests. So in order to adjust that, we add a prefetch buffer in the Alluxio client side. So it means that for every read, if it's less than 1 megabytes, we will read 1 megabytes and hold in the buffer. So the small reader can just fetch the data from the buffer. The below is a diagram. So the number here, 2 billion requests per second, is how many read we read from the buffer in one Presto cluster. And the bottom diagram shows that how many actual requests we send to Alluxio worker. So yeah, it's even more than 1,000 times. So with such prefetch mechanism, so we speed up we improve the performance, and Alluxio worker can provide a pretty good throughput. Here is the setup and impact. So because that's the first stage of our distributed cache, so we set up a production cluster with 112 cache nodes. It had about 1 PB capacity, and we enabled 2 Presto cluster to read from the distributed cache. Yeah, in the first diagram, we can see that the yellow line here is read from the Alluxio cluster. That's the distributed cache. So it totally depends on the traffic, whether the query read from hot table or not. So especially for that spike, right? So the majority of traffic will come from the Alluxio cluster. And overall, in on-premise, the cache throughput can hit 200 gigabytes at peak. For example, in that diagram, we reduced the HDFS throughput a lot at the moment we launched the cache. So it relieved the HDFS IO saturation in HDFS, and also give us more flexibility in the cloud migration. In that case, we can decouple the storage migration and the computer migration a little bit. Okay, for next step, I'd like to hand over to Beinan.
Thank you, Yangjun. I'm Beinan from Uber. Today I will cover our journey about using Alluxio cache on cloud. And just as Yangjun mentioned, when we migrate to cloud, we are seeing new challenge, something like the higher limitation of our egress and also the cost of GCS Class B operation cost. So we enhance the open source Alluxio to achieve a much better data locality for Presto. I will cover more details in the following slides. Okay, next one, thank you. I think the first challenge here is the cost. If we want to deploy a real large scale Alluxio on cloud, the machine will be the huge cost. So we are thinking, we can co-locate our Alluxio with Presto because somehow Presto is not using their local disk, right? For most Presto cluster, we won't enable the data spill. So by co-located with the Presto cluster, we can just utilize the local disk of every Presto node. And by watching our metrics, looks like the Alluxio only need 6 or 8 CPUs per node. They can handle the traffic pretty well. So by doing so, can highly save our cost. And because we co-located with Presto, so we can share the scale of Presto. So now in our cloud, we have 10 times more node got deployed. Another challenge is the GCS connector. It's not something like HDFS. So when using GCS, it's hundreds buckets there. So we have a large pool to maintain this kind of thing. So we also enhance a little bit here to make our file system to support hundreds of the file system, or we can say the physical bucket instance. Go to the next page. Just as I mentioned, we scale up the cluster size. We're using collocations, and we scale the cluster size by 10 times. But the issue here is we have more Alluxio server, also we have more Alluxio client. So in case, if we still want to maintain the same membership, now we are using the etcd to maintain the membership. The etcd will receive much more traffic because of each worker need to register itself as a member to our hash ring, and each client need to access the etcd to get the full list of worker to construct the hash ring on the client side. With the much higher traffic, we can see sometimes, it's not always, sometimes we are seeing failure on etcd side. But from the open source Alluxio, the etcd membership management is in the critical path. So if it failed, you will see some failure when you read the data. We change it more like asynchronized lazy membership fetching, and also we implement a fail open design, which means even though sometimes the fetching it failed, we can still use the old hash ring to fetch the data. And also by doing so, we are seeing the traffic pattern to the etcd is much smooth. There's no spikes at all to protect the etcd cluster. Okay, let's go to the next page. On the other side, when we use Alluxio on-prem, we still guarantee that the data freshness, but we are using something we call metadata validation. We keep the metadata for each file on each worker. The issue here is sometimes there might be some risk condition because sometimes maybe the metadata got updated, but the data is still old. Maybe someone updated the data at the same time. So on cloud, we enforce a versioning to each cache entry. Something like in the cache key, we put the last modified time into the cache key. So why we call it end-to-end file versioning, just because this last modified time actually is coming from the coordinator. If you know how Presto is working, the Presto coordinator actually they list all the files in a folder, and meanwhile it will also get the last modified time of each file. When the coordinator do the dispatching, it will push down this last modified time with the file name into each worker. So now that each worker have this kind of last modified time, we can say this versioning information. It combines these two together to find the right worker. And if the last modified time got changed, which means the file got changed, it will go to another cache key, right? Because we combine it together, so it will go to totally different data entry, and the old data, although we can say the still data, will got evicted. We call the passive data eviction. That's how it works. For this approach, for each file entry or cache entry, it's immutable. So they're totally avoid the risk condition and the corrupt data to read in the cache, and also the performance is much better because we skip the metadata validation, or we also skip the metadata store in each worker. Let's go to the next page. On the other side, we are using a semantic cache filter here. We call time bucket based cache filter. So we are using a chain of the sliding window, not just single sliding window. We are using multiple sliding window. Each sliding window will record the count of each partition. The count means the read count, how many times you read from the client side, you read from its partition. And based on this kind of stats, we can make a decision which partition is more valuable to cache. Because if you know Presto, if Presto want to read the partition, it will read the entire partition. Am I right? So in this case, we add the cache filter at the partition level, and we are using a sliding window, which means we can keep the access pattern in the past 2 days or 7 days, totally based on your traffic pattern. So by doing so, we are seeing a much higher cache hit rate from 40% to more than 80 or sometimes even 90% cache hit rate. Let's go to the next page. Here is some real metrics we collected from our real production. For this deployment, we are seeing 1,200 cache node, and it's around actually more than 2 petabytes for the cache capacity. there's 5 Presto cluster hitting this shared cache cluster. That's also why our cache hit rate is much higher than the local cache, because multiple Presto clusters are sharing one Alluxio cluster. You can see the chart on the right. The green one is the outer node, and the yellow ones is the load, the read from cache. You can see for most of the specs, the cache can eliminate the specs and can reduce the traffic. So you can see the maximum total traffic is 8 TBps, but the cache can handle 6 TBps of them. So the traffic go to the egress got highly reduced. So the maximum to the egress is just 2 TBS. So that sometimes that is okay for most of PBS, but if we without the cache, it will a huge challenge to the egress. And also here is actually the raw data from Presto side. If we're talking about network bandwidth, we're talking about the real data read from GCS. It's much higher than this value because there's some read amplification from the GCS connector. Not just prevent the spikes during the traffic peak, we are also saving our cost. Because as I mentioned, we pass through the last modified time and some metadata from Presto worker to the from Presto coordinator to the worker. So we don't need to get metadata to the GCS anymore. We can just read the data from Alluxio. If the cache hit, we save the metadata cost. We also save the data read cost. We also support the regional failover somehow to when some disaster happened into our cluster. Let's go to the next page. Okay, I will talk a little bit about the next. What's our future work? Actually, some work is already started. Some ongoing work. We will do the integration with vlogs. Currently, we're using Java client, but in the near future, we will have a native client to integrate with vlogs. So vlogs can have exactly the same feature of our Java cluster. And also, we will reduce the resource usage. We will improve the performance. We will also have a native server. Because currently the server side is still Java. We may make a native or C++ or Rust server, and it can also highly reduce the resource usage on the server side. I mean, we're talking about the co-location. We really want to save the resource usage. Yes, I think that's probably everything we want to cover today. Let's go to the next page to go to the Q&A session. If you have any questions, I think you can put it into the chat, or there's some question board. Okay, thank you.